Soaps. Soaps are the higher fatty acids of sodium or potassium. These are higher fatty acids of sodium or potassium ions, and these are formed by the hydrolysis of higher fatty acids or oils in presence of some bases like sodium hydroxide or potassium hydroxide. For example, if we hydrolyze glyceryl ester is this CH2CO C17H35. Three such units are there. So CO C17H35 CH2O CO C17H35. This is glyceryl ester. So if we hydrolyze glyceryl ester in presence of sodium hydroxide, we'll get sodium stearate. That is C17H35 COO minus Na plus. This is sodium stearate. In addition to that, we'll get a glycerol molecule which is CH2OH, CHOH, CH2OH. This is glycerol molecule. So this is a typical preparation method of soap molecule. Then on the basis of the nature of the oil we are using for the preparation of the soap and the purpose of the soap, we can divide soap into different types. That is based on purpose and quality of oil. Different types of soaps are there. The first one is hard soap. Hard soap means the soap having a hard nature. That is, the quality of the oil used in hard soap is very less. That is very low quality oil is used for the preparation of hard soap. And the alkali used in the hydrolysis process is sodium hydroxide, and these are used as washing soaps. Then the second one is soft soap, that is a soft nature soap. The quality of the oil used is very high, so high quality oil is used here. And the base used in the hydrolysis process is potassium hydroxide. Basically, these are used as the toilet soap and shampoos, etc. are coming under soft soap category. Then the third one is transparent soap. So these soaps having a transparent nature, and in transparent soap, glycerol in alcohol is used for the preparation of transparent soap, and the insoluble part in the soap is filtered off during the preparation process. That is why these soaps appear as transparent soap. Then the fourth category is medicated soap. Medicated soap containing some germicidal reagents. So that is why this is categorized as medicated soap. Examples are mercury soap, neem soap, etc. Then the fourth category is metallic insoluble soap. Metallic insoluble soaps. So Normally, metallic insoluble soap is different from ordinary soap, and the purpose of these soaps are entirely different. These are not used for cleaning purpose. It is not used as not used for cleaning purpose. That is, their purpose is a little bit different from ordinary soap. These are usually used as lubricants or waterproofing agents for waterproofing, etc. Examples are nickel soap, magnesium soap, calcium soap, etc. are coming under metallic insoluble soap category. If we talk about the cleansing action of soap, normally a soap molecule containing a hydrophobic tail and a hydrophilic head. This is hydrophobic and this tail and this head is hydrophilic. Or we can say tail is a non-polar part in a soap molecule. It is non-polar and the hydrophilic part is polar. And coming to the nature of dirt, dirt is actually oil or grease. So when we apply soap to dirt, what happens is the hydrophobic part in the soap molecule come and attack the dirt, and the hydrophilic part projecting outwards and form a globular structure like this, and it is known as micelle. By mechanical and physical actions like rubbing and tumbling, the micelle will be dislodged from the cloth. So by using enough water, we can easily remove dirt from cloth. And this molecule dislodged from the cloth in water form an emulsion. There are some situations in which soap cannot perform well as a cleansing agent. For example, in hard water, the performance of soap is feeble because with hard water they form their calcium or magnesium salt. For example, sodium stearate. Sodium stearate is C17H35COO Na. This is sodium stearate. When sodium stearate is applied to hard water containing magnesium ion, this magnesium ion replies the sodium and form C17H35COO. Here magnesium is 2 plus bivalent ion, so twice Mg. So we need 2 soap molecules. Magnesium stearate will be formed. And this magnesium stearate is insoluble in water and will not form lather. Same way, we can write the reaction of calcium ions with the sodium stearate or any other molecule. Calcium is here, then the molecule formed is calcium stearate, that is C17H35COO twice. Calcium will be Ca, will be the new soap molecule formed there. There are some detergents which remove or which act well in hard water also. Detergents are the broad term which is used to mention the cleansing agent or surface active agents which remove dirt. Here there is a special type of detergent or surface active agent which are known as synthetic detergents, synthetic detergents or synthets. If we talk about the structure of synthetic detergents or synthets, they are also containing a hydrophobic part and a hydrophilic head. Hydrophobic and hydrophilic or non-polar polar part. But difference from soap is the hydrophobic part in soap is either natural oil or fat. But in synthets, instead of natural oil or fat, we use synthetic reagents, synthetic materials. So from this, we can differentiate the soap and the synthets, that soap containing natural oils or fats, so it is easy to degrade. So degradation of soap is very easy. But coming to synthets, it is synthetic reagents. So degradation is difficult. So using synthets for washing is not a green method because it remains in the soil for a long time. But soap degrade easily. The cleansing action of detergent is little bit different from soap. Actually, this is dirt, that is oily natured substance. So when we apply detergents, that is synthets, into a cloth containing dirt, what happens is this synthets reduce the surface tension. So synthets normally reduce surface tension, and these synthets absorb on the surface of cloth. Adsorption occurs. So the steps occurs here is first one is adsorption of synthets. Then second process normally occur along with the adsorption is reduction of surface tension. Reduction of surface tension. So when surface tension when surface tension reduces, what happens is the dirt molecule or the oil molecule converts to its droplets. So conversion of oil into droplets. So by applying water or by physical actions like tumbling and rubbing, we can easily wash out the dirt from cloth. Removal of dirt by physical process. So this is the cleansing action of synthet. Then the type of synthets. Based on the nature of the hydrophobic part, synthets are classified into two. The first one is alkyl sulfonates and the second one is Aryl sulfonates. Alkyl sulfonate synthet means these are the sodium salt of sulfuric acid ester. And these are formed by the esterification of sulfuric acid with long chain alcohols. with sulfuric acid, and the hydrolysis of the ester formed here in presence of sodium hydroxide gives these synthets. For example, sodium lauryl sulfate. Sodium lauryl sulfide. These synthets are formed by the esterification of lauryl alcohol, that is CH3 CH2 9 times CH2OH. Sulfuric acid is here. So during esterification, water molecule is eliminated from here and we'll get molecule like this, CH3 CH2 9 times CH2O SOOH. And by the hydrolysis in presence of sodium hydroxide giving sodium lauryl sulfate, that is CH3 CH2 9 times CH2O. We can shortly write this as SO3, and sodium will replace this hydrogen and it form molecule like this, Na plus and SO3 minus. Or we can write it as SO2 O Na, O minus and Na plus. This is sodium lauryl sulfate. Then the next one is Aryl sulfonates. And these are the sodium salt of alkyl benzene sulfonates. That is, these are the benzene sulfonates having an alkyl ring. It's the hydrophobic part, and Na plus and O minus. This is the basic structure of aryl sulfonates. A typical example is sodium dodecyl sulfonate. Sodium dodecyl sulfonate, and here this R group will be CH3 CH2 9 times CH3. So if R group is this, then this is known as sodium dodecyl sulfonate. And usually these are prepared by the Friedel-Crafts reaction. That is, example, if you are going to prepare sodium dodecyl sulfonate, then we have to take one dodecene. The one dodecene is the CH3 CH2 9 times CH2, and we have to react this with benzene, anhydrous aluminum chloride. R group in presence of aluminum chloride, anhydrous aluminum chloride, react with benzene molecule, and the substitution reaction will take place and we will get this molecule, that is benzene having a CH3 and CH2 9 times CH3. So when we react this with sulfuric acid, we'll get the sulfonate of this compound, that is this here we'll get an SO3H group. So here we'll get an SO3H group, and this R dodecyl group will be here, and this group will be here, and by the hydrolysis in presence of sodium hydroxide gives sodium dodecyl sulfate. I'm going to rewrite the reaction here, that is CH3CH2 9 times CH double bond CH2 on Friedel-Crafts reaction with benzene and presence of anhydrous aluminum chloride. We'll get a molecule like this. Here CH3 CH2 9 times CH and CH3. So when we react this with sulfuric acid and the product is hydrolyzed with the sodium hydroxide, we'll get the sodium lauryl sulfate molecule, that is CH3CH2 9 times CH3. Here we'll get SO3Na, SO3 minus and Na plus. So this is the entire reaction. Then the next classification is based on the nature of the surface active part. Nature of surface active part. So based on the nature of surface active part, these are classified into three. The first one is anionic surface active. Anionic surface active. Then second one is cationic surface active. Then third one is non-ionic surface active. Non-ionic surface active. So the first one is anionic surface active. The anionic surface active surfactants are usually sulfates of long chain alcohols. These are usually the sulfates of long chain alcohols. Or we can say, or sulfonates. Here in these synthets, the polar part is OSO3Na. This OSO3, O minus Na plus. And the non-polar part may be long hydrocarbon chains. So non-polar part may be alkyl group or aryl group. So here we can say the examples are lauryl sulfonates, and sodium dodecyl sulfates are examples of anionic surface active synthets. Sodium dodecyl sulfates, etc. are examples of anionic surface active agents. The second one is cationic surface active synthets. Up to this, we talk about the synthets which having the hydrophobic parts containing negative charge. But here in cationic surface active agent, the surface active part, that is the hydrophobic part, contain positive charge rather than negative charge. For example, this molecule C6H5 CH2 NCH3 CH3 C8H17. Here nitrogen is tetravalent, so positive charges here, and this is balanced by Cl minus ions. So this is a particular example of cationic surface active syntax, and this is benzyl dimethyl octyl ammonium chloride. So this is a typical example of cationic surface active syndet. The third one is non-ionic detergents. Here, this detergents do not have any ionic part, do not have ionic part, but they are polar. So we can say these are polar covalent molecules. Polar covalent molecule. For example, CH3, CH2 14 times, COO, CH2, C, CH2OH, CH2OH, CH2OH. This is pentaerythritol palmitate. Simply looking, we cannot see any polar and non-polar part in this molecule, but this molecule is polar. If we look this part, this molecule is polar, and this is a hydrophobic part, and the remaining part is hydrophilic. So this part is soluble in water, and we can use this non-ionic detergent for cleaning purposes. For example, dishwash liquid are coming under non-ionic detergent category. So these are all about the surface active agents.